In this video, we will finish up our investigation into Taylor and Maclaurin series by seeing how they can be applied to answer a few common questions. To begin, the previous list we've had of common Maclaurin series that we should make sure to have committed to memory. That is, can we recall them if we need to use them? So a very typical question. Find a Maclaurin series for some given function, and then use that Maclaurin series to evaluate some integral in terms of an infinite series. So let's start off with x cosine of x cubed. So we're going to begin with kind of the building block here. We're going to think cosine is a function with a common Maclaurin series. So cosine of something is equal to the sum from n equals 0 to infinity, and the intuition here is cosine is an even function. So this will be minus 1 to the n, something to the 2n, all divided by 2n factorial. So if we want to get cosine of x cubed, we can simply use that as the something that we plug in. So this would be the sum from n equals 0 to infinity minus 1 to the n, x cubed raised to the 2n, all over 2n factorial. And at this point, we really need to do two things. The first is we could simply add an x out front, but then we need to somehow simplify and combine everything inside this power series. So we need to think about moving the x inside and also combining the powers of x. So putting this all together, x cosine of x cubed is the sum from n equals 0 to infinity minus 1 to the n. And let's start off with the x cubed raised to the 2n. If you have a power raised to a power, you multiply. So x to the 6n. And because we're hitting it with another x, the one coming from out front, we need to put a plus 1. And this is all divided by 2n factorial. So this is part one of the question. We have a Maclaurin series representation for the function x cosine of x cubed. As a side note, this is a power series, so it has an associated radius of convergence. If you wanted to find that radius of convergence, we could always do so by applying the ratio test. In this case, you will find that it is infinity. Now we need to evaluate the integral. So if we want to anti-differentiate x cosine of x cubed, what we can do is replace that function with its power series representation. Now the function itself would be quite difficult for us to integrate, but we've seen previously that we can integrate power series very conveniently. We can take that integral and really plug it inside the summation. That is, we can write this as the sum from n equals 0 to infinity of the integral of minus 1 to the n, x to the 6n plus 1, all divided by 2n factorial. And in terms of evaluating this integral, there's really only one thing we need to worry about. We have x raised to a power. So if we want to anti-differentiate x raised to a power, we take its exponent, we add 1 to it, that's our new power, and we also divide by that number. So we're going to have minus 1 to the n, x to the 6n plus 2, because we've added 1, divided by 2n factorial, multiplied by 6n plus 2. And then lastly here, keep in mind whenever you are evaluating an indefinite integral, we always need to include that constant of integration, the plus c. Note, once we came up with this power series representation, anti-differentiating was actually quite convenient because we can take the integral, plug it inside, and it comes down to anti-differentiating x raised to a power. So add 1, divide by that number as well. Another common example involves looking at some given series and somehow determine what the sum is by relating back to one of our familiar or common Maclaurin series. And the observation that I would like to make here is we have something to the nth power over something factorial. And immediately what jumps to mind would be the power series representation for e to the something. So recall e to the something is the sum from n equals 0 to infinity, something to the n, all divided by n factorial. So let's see if we can rewrite our power series in this form. So we have the sum from n equals 0 to infinity, and using properties of exponents, 2 raised to the power 4n can be simplified or rewritten as 2 to the 4th raised to the nth power. So the thing that we are plugging in for the blank would be 2 raised to the 4th power. So by comparison, this is e raised to the number 2 to the 4th, which is also more conveniently expressed as e to the 16th. To answer a question of this form, it really goes back to those common Maclaurin series. Can we recognize which formula we are comparing to and what we are plugging in to that given formula?